I welcome you all in RC design class. In this lecture, I shall discuss about the slab, how the slabs are designed. You know that in building, different structural elements are used like beam, column, slab, footing, and uh, slab is slab is a structural unit which is used to cover floor and roof of building. Now here the structural plan of typical floor is shown here, means the plan view is drawn and uh, only the structural members are shown here. The structural members are, what are the structural members? Beam, column and slab. Now uh, this in this plan two type of beams are uh, used. One is primary beam, which is which is raised on uh, column. The another is secondary beam, which is, so this one is secondary, this one is primary beam, which is raised on primary beam, and this portion is called slab. The slab is supported on beams. The slab is integrally connected with beams. Now the two type of panels are considered, the panel 1 and panel 2. The panel 1 size is 1.5 meter and 4 meter, whereas the panel 2 size is 2.5 meter and 4 meter. Now the shorter uh, and shorter longer span is denoted by LY. So the panel 1, the longer span of panel 1 is how much? That is 4 meter, and it is denoted by LY, and the shorter span is denoted by LX. Okay. Now here you see that two type of panels are considered, and if you take a ratio of longer span and shorter span, then you find that the panel 1 is more than 2. Okay, the ratio of longer span to shorter span is more than 2, and the panel 2, the ratio of so that this ratio is called aspect ratio. So longer span and shorter span ratio is less than 2. So the two type of slab we have considered. The panel 1, which have ratio, means the aspect ratio is more than 2. The panel 2 has aspect ratio less than 2. So here the typical floor plans are shown here. The panel 1 is called panel 1 is called one-way slab, and panel 2 is called two-way slab. Okay, so so here the one structural plans is shown here, and in this plan the beam, columns, layout are shown, and also the panels are shown, and the two type of panels are considered. The panel 1 has more than the ratio is more than 2, whereas panel 2 less than 2. So when the aspect ratio is more than 2, is called one way slab, and panel 2 with the aspect ratio less than 2, the slab is called two-way slab. And another point you note that slab is a 2D element, because this will have the two dimensions. Two dimensions are considered, means the length and width, and it is supported on, so just I I have shown in previous slide, the slab is supported on, either it supported on masonry wall or on beam or on directly on column. So basically three type of support are considered. Either it is supported, either the slab is supported on masonry wall or on beam or on directly on column. And what load is carried by the panel, what load is carried by the slab, that is the gravity load. So gravity load, you know, this is a dead load and live load. Dead load and live load is called gravity load, so which is acting vertically downward and it is acting normal to the surface. So this load is transferred to the support, because the slab is supported on beam, so whatever the load is acting, so this load is transferred to beam. And how the load is transferred? Load is transferred to the support primarily by flexor, means the by bending load is transferred to the support. Mainly load is transferred by flexor means the by bending, whereas in beam the load is transferred to the support by shear and flexor. Now you see that here the load is transferred, load dispersion of slab is shown, and code said that load uh, dispersed at 45-degree angle. So it means you see that this is a panel, the panel is supported, the four side is supported on beam. Now if the load dispersion angle is 45-degree, then this much of load is transferred to this beam, whereas this much of load is this triangular load. This is a rectangular panel, this triangular load is taken up by this beam, whereas this trapezoidal load is taken up by this beam, and similarly this load is also taken up by this beam, another this trapezoidal load. So you see that if the panel is rectangle, then the triangular load distribution and trapezoidal load distribution took place. So trapezoidal load is taken up by the longer beam, by longer beam, whereas this triangular load is carried by this beam. Okay, this much of load is transferred to this beam, whereas this much of load, this trapezoidal load is taken up by the longer beam, whereas this triangular load is taken up by the shorter beam. So this load dispersion angle is given. So in this way the load dispersed, it is given in IS 456 page 41. So here the how the load is dispersed, how the load transferred to the support, it is shown in figure 7 in page number 41. So as I have said, the slab has the two type. Slab has two types. One is one-way slab, another is two-way slab. So what is one-way slab? If the aspect ratio, means the ratio of longer span to shorter span more or equal to 2, that time slab is called one-way slab, and the spanning in one direction. Means if the aspect ratio is more than 2, so so the this span is greater and the load is transferred in this way. So you see that the shorter beam, this beam carry only this much of load, means the very small load is taken by this beam, and the maximum load is taken up by the longer beam. Okay, this beam is carrying the maximum load, and you see that how the load is transferred. The maximum load is transferred in this direction. Okay, so you know that the slab is a two-dimensional element, so the two movements are take place. Two movements are developed. Two flexural movements are developed. One is shorter span movement, another is longer span movement. So mx means the movement about x-axis. Okay, if the bending took place uh, in this direction about the x-axis, and the bending is maximum at the middle, whereas the my is the longer span movement, the movement about y-axis. So means the longer span movement developed, and uh, and if I compare the mx and my in one slab, you see that my is very less than mx. So slab is designed for only one movement, means the for only in shorter direction movement, and my is ignored because the as the aspect ratio is more than 2, and along longer direction the small uh, load is transferred, the maximum load is transferred in longer direction, I mean the shorter direction. So that's why the moment developed mx is computed, and my, which is not considered because the value is small, so we can ignore it. And when the aspect ratio less than 2, so then what happened, then spanning in both direction, means the in both direction load is transferring, I mean the significant amount of load is transferring in both direction. Okay, so the both span are considered. You see that as it is 2a, so this triangular load is taken up by this beam, whereas this trapezoidal load is taken up by this beam, as the load dispersion angle is 45-degree angle, and the both movement are significant. Okay, both movements are significant. So slab is designed for both movement, means the slab is designed in both direction. So in 2a slab, the both spanning are considered, whereas in 1a slab only the one span is considered, is the shorter span, because the longer span movement is very less compared to shorter direction movement. So that's why it is ignored, and the slab is mainly designed for mx, means the in shorter direction movement, whereas the 2a slab, the both movement are considered, and the both span are considered, longer span and shorter span are considered, whereas in 1a slab only the shorter span is considered, because the along the longer direction the small load is transferred. Next, another point you note, that slab is mainly designed for flexure. Okay, you know that the beam is designed for flexure as well as shear forces, but slab, because you know that the load is transferred to the support primarily by flexure, so slab is mainly designed for flexure, and the shear resistance, slab has large shear resistance, so that's why there is no need of shear reinforcement. So as the slab has large shear resistance, so that's why there is no need to apply shear reinforcement. So only the design slab is designed only for flexor, is the only for bending moment, not for shear force. As the slab, you may check it, but but the uh, but we design the slab mainly for bending, not for shear. Now, how the slab is analyzed? You know that slab is a 2D element, so slab behave like a plate, and this theory is used, yield line theory is used for the analysis of slab. And this theory is the accurate method to compute moments in slab, but the drawback is this analysis is not carried out by the designer, as it is difficult, okay, lengthy and time taking process. Okay, it will take time and also it is difficult, lengthy, so that's why this analysis, yield line theory is not carried out for the analysis of slab. uh, so so that's why the code, due to this problem, code suggests simplified formula to compute moments. So that's why the code uh, give a formula to compute moments. And one thing you note, for the sake of convenience in the calculation, 1 meter width is considered. Okay, we are calculating moments reinforcement per meter width. Now, as the in 2A slab, the two moments are acting along the moments along longer direction, and movement along shorter direction. So the mx and my, the both movements are developed, both movements are produced under load. So due to this movement, torsion is developed. So when the two movements are developed, so due to these movements, the torsion is developed. You know that torsion is a force which is, this is also a turning force which is applied about the axis. The twisting took place, so the torsion is developed, and it is maximum at the corner region. So in the corner region, the maximum torsion developed. Now due to this torsion, the corner is lift up. Okay, it will lift up. So based on such phenomena, slab has two categories. Two type of slab are considered based on the lifting of the corners. The slabs has the two category, means the 2A slab has two category. One is restrained slab and another is unrestrained or simply supported slab. Okay, so what is restrained slab? When corner of slab is prevented from lifting, such type of slab is called restrained slab. Another is when corner of slab is not prevented from lifting, such slab is called unrestrained slab or simply supported slab. So this classification, the definition of such slabs are given in IS 456/2000. You see that here this is a slab, the 2A slab. You know that in 2A slab the spanning are in two direction. The both span are considered, longer span and shorter span. And this slab has two type 2A slab. one is restraint slab. When the corner of a slabs are prevented from lifting, it is given in IS 456 2000 page number 90. Go to annex D. Okay, and maximum bending moment is computed using this formula mx and my. The formula is alpha x, then w, and then lx square. Okay, mx and my. So for computing the both moment, the shorter span is considered, that you note. Okay, only the coefficient are different. Alpha x, which is the bending coefficient along shorter direction, and alpha y, which is this is mx, equal to, which is this coefficient along shorter direction, and w is the design load per meter run. Okay, and lx is shorter span. So for computing the both movements, the shorter span are considered as per code, and this is a simplified formula has mentioned in code to compute the moments in slab. And now, as it is restraint slab, means this is a corners of the slab are prevented from lifting. So it means what? It means we are using the torsional reinforcement, okay, to prevent lifting of the corner, because due to the torsion is developed, and due to the torsion corner is lifted up. Now this tendency is prevented by using the torsional reinforcement. Okay, so restraint slab means we are applying the torsional reinforcement as the corners is prevented from lifting. Now another type of slab is given, that is simply supported slab. So which is unrestrained, means the corners you see that when simply supported slab do not have adequate provision to resist torsion, means that we are not using any torsional reinforcement in simply supported slab. And what happened? Due to this, the corners and at corners, and to prevent the corners from lifting, so it will not prevent the lifting of corners. Okay, the corners are not prevented from the lifting, although the torsion is acting. So here in restraint slab, the torsional reinforcement are used, whereas the simply supported slab, torsional reinforcement are not used. Here the tables are given to compute alpha x and alpha y. To compute alpha x and alpha y, this table is given in that is table 26 and page number 91. So here in table 26 the coefficient values are given. So you see that the first column here, the 9 cases are mentioned, 9 cases are considered, and type of panels and moment considered. The panels means here the edge condition are given. This is the edge condition, or boundary condition. Edge condition given and the aspect ratio Ly by Lx. So for different values, different aspect ratios value, the moment coefficient given. This is for shorter direction, shorter span coefficient, and this is for longer span coefficient. And for all aspect ratio that you check, for longer span bending coefficient, for all aspect ratio the values remain same, and for different age condition the values are given. So the first I consider the interior panel. So interior means when the 4 age, this 4 age, the panel 1 is a interior panel. This is a case 1. Okay, this is a P1 is a case 1, panel 1. Here the 4 edges are continuous. Okay, 4 edges are continuous, so this panel is interior. This edge is continuous, then this edge is continuous, this edge is continuous, and this edge is continuous. So this is a interior panel. And the negative moment at continuous edge, so you know that as this panel is continuous over the support, so due to the continuity, the negative moment is developed in the support region. So here the negative moment is developed, negative, and on span the positive moment is developed. So that's why the negative moment coefficient given, which is negative, is the hogging moment take place, and you have to apply the steel at top, whereas the positive moment took place on span. Next case 1 shortage, here the continuous given but the printing mistakes has made. So this is the actual case is 1 shortage discontinuous. Okay, the age is 1 shortage discontinuous. Now the as per so here the floor plan are shown, the different panels are shown. So this panel 2, 1 shortage discontinuous. So how the 1 shortage discontinuous? This is a shorter direction shortage, and which is not continuous, discontinuous. Okay, where other 3 are continuous. So here the 1 shortage discontinuous. Next, the 1 long edge discontinuous, means that this long edge is discontinuous. Okay, so that's why the positive moment developed in span, on span the positive moment developed, and in the continuous edge the negative moment is developed. So here the negative moment is developed and the positive moment developed in the span or in the middle. Okay, the maximum is considered. So maximum positive moment took place at the middle. So the span moment is always positive and support moment is negative. 2 adjacent, so this is third case. The fourth case, when the 2 adjacent is discontinuous, this 2 adjacent edge is discontinuous. So this is a panel 4. The span moment is positive, so that's why the positive span moment at mid span and negative moment at continuous. So this panel is continuous over this edge. So here the negative moment is developed, here the negative moment is developed. So that's why the coefficient are given, and using the formulae you find out moments, positive moment. Find out span moment and support moment. And in shorter span also the positive coefficient given. So from positive coefficient you get positive moment, and this is a negative. So positive moment you get the positive positive coefficient, you get the positive moments, whereas the using for negative coefficient you get negative moments. So this again the table 27 is given. This is for simply supported slab where the torsional reinforcement are not used. Using the formulae same, alpha x w lx square, alpha y w ly lx square, and as it is simply supported slab, so here this is equal, not minus, equal. So for different aspect ratio, the alpha x and alpha y values are given. As it is simply supported, so that's why no negative moment is developed. Okay. So as it is simply supported means the four edges are discontinuous. So you see that this four edges are discontinuous, so means only the span moment is developed and this edge is simply supported. So at the simply supported end there is no negative moment or moment is zero. Okay. If I draw the bending moment of simply supported beam or slab, so what is the bending moment? The bending moment is 0 at support and maximum at middle. So bending moment is 0. So that's why there is no negative moments, only the span moment is given. Okay, no negative moment is not mentioned here as it is simply supported, because at the support the moment is 0. So bending coefficient for 2A slab, so just I have discussed, I have already discussed in previous slide. Again I repeat, the bending coefficient for 2A slab, when the slab is torsionally restrained, means the restrained slab, the table 26 is mentioned in IS 456 2000 to determine bending moment for different edge condition and different aspect ratios. So this coefficient depend on different edge condition, means the for different edge condition, different boundary condition, and depends on Ly by Lx and boundary condition or edge condition. Okay, depend on this coefficient, depend on boundary condition and aspect ratio. So this slab is torsionally restrained, so it means you apply the torsional reinforcement in the corner to resist torsion. Okay, to resist the torsion you have to apply the torsional reinforcement in the additional torsional reinforcement you have to apply in the corner region. You see that, so the edge condition, for different edge condition and for different aspect ratio, the coefficient are given. And the 2A slab has the two moments, the mx and my, and the moments are positive and negative. Positive moment means this is a span moment, so you have to apply the steel at bottom, whereas the support moment near the edge, so at support moment means the where the I mean the when the panel the continuous edge, at continuous edge you have to apply the negative moment is developed, and you have to apply steel at top. Another type of slab that is torsionally unrestrained, again in table 27 is mentioned in IS 456 2000 to compute bending coefficient for different aspect ratio and edge condition. As it is simply supported, so it means the four edge is discontinuous, Okay, the 4 edge is discontinuous. So it means at support and also the at support there is no moment, because you know that the in simply supported beam at support the moment is 0. So that's why there is no negative moment, there is no moment at support, only the span moment is considered to design simply supported slab, and no torsional reinforcement is used. Now in torsionally resistant slab, court suggests three different requirements of torsional steel are used in three different corners. So the three different corners are mentioned where you have to apply the torsional reinforcement. The corner 1, corner 2 and corner 3, which is shown in previous slide. So this is a corner 1, corner 2 and corner 3. As per court said you see that corner 1, torsional reinforcement shall be provided at any corner where the slab is simply supported on both edges meeting at the corner. So this is a corner type 1. It shall consist of top and bottom reinforcement, each with layers of bar placed parallel to the side of the slab and extending from the edge a minimum distance of 1/5 of shorter span. The area of reinforcement in each of these 4 layers shall be 3/4 of the area required for the maximum mid-span movement in the slab. So it means this corner, as per clause D 1.8, in this corner you have to apply the reinforcement, and the in area the length area is Lx by 5, 1/5 of the shorter span, and you have to apply the reinforcement in 4 layers, and each layer consists of 0.75, means the 3/4 reinforcement used in the mid span, 0.75 of AST. So that I explain later when we discuss the design problem. So that time I shall discuss here, that time I discuss. Now the another type of corner C2. So what reinforcement you apply in corner 1, just you apply 50% reinforcement. What reinforcement are used here? The 50% reinforcement are used in corner 2. Whereas as per code in corner 3 no torsional reinforcement are required. Okay. So basically in corner 3 the torsional force are balanced each other. I mean here the torsion developed in this corner. Now this force is balanced by this force which is again developed in panel 1. Again this force is balanced by this force, this torsional force. So the these torsional forces are balanced each other. So that's why as per code said in corner 3 there is no need of torsional reinforcement, whereas in C2 you see that 50%. Why 50%? Because this component and this component is balanced. So that's why only for one component you have to uh, apply the torsional reinforcement. Okay. It's the like the torsional force is acting like this. If I resolve these forces into component, horizontal and vertical, so you see that this vertical component and and these panels vertical components uh, balance each other. So that's why in corner 2 50% reinforcement is required, whereas the C3 all the torsional forces are balanced each other. So that's why in corner 3 there is no need of torsional reinforcement, and in corner 1 you have to apply the maximum torsional reinforcement, and the torsional requirements are given, the how much reinforcement you have to apply, that is mentioned, and in C2 the 50% and C3 there is no torsional reinforcement. Clause D 1.8 for C1, clause D 1.9 for C2. Just you go through the go through this clause and you read properly, and you get uh, the torsional requirement, and C2 C3 are given in code. Like beam, in slab also you have to check deflection. The allowable deflection limit is mentioned in code. You see that for 2A slab of shorter span up to 3.5 meter with mild steel means that is Fe 250. Fe 250. Okay, the span to overall depth, the ratio is span means the shorter span and overall depth. So that you note, for checking the deflection shorter span is always considered, and also to compute moment the shorter span is considered. And so satisfy the depth span by depth which should be less than uh, vertical deflection limit for loading class up to 3 kN per meter square. Loading class means the live load. Okay, up to 3, the simply supported slab, 35 for simply supported slab, the deflection limit is 35 L by D ratio, and for continuous slab the deflection limit is 40. For high strength deform bar, if I use more than Fe 250, instead for Fe 415 and Fe 500, the values given above should be multiplied by 0.8. So this value, if I use Fe 415 or Fe 500, then you multiply 0.8 with the above value. Okay. Next, when you design slab, so that time, so few point has to be remembered. For the convenience, load, bending moment, shear force and reinforcement is calculated per meter width. Reinforcing, not reinforcing, this is a reinforcement. The reinforcement is calculated per meter width. 1 meter strip width is considered on slab, and loads are estimated per meter width as shown below. So you see that the load, bending moment, shear force and reinforcement is calculated per meter width. This is a 1 meter strip we have considered, which have width. This is a 1 meter strip width. Strip we have considered, the width is 1 meter, and we calculate the reinforcement per meter width, so we can get easily total reinforcement. Okay, just multiplying the actual width, we get the total reinforcement. So here the unit width is considered for the convenience. The 1 meter strip width is considered, and the reinforcement as the two movements are developed. Okay, in 2A slab, the both two movements are developed, shorter moments and longer moment in 2A slab. So that's why you have to apply the reinforcement in both direction. Okay, along longer direction you have to apply the reinforcement, as well as reinforcement also apply in shorter direction. These are reinforcement along longer direction, then also reinforcement you apply in shorter direction. In both direction, reinforcement has to be placed. Okay, and which is just above the one after another we giving the reinforcement. Also we check the spacing of reinforcement bar as mentioned on code. Okay, the reinforcement spacing is also mentioned. You see that the horizontal distance between the parallel main reinforcement. So between the two reinforcement, the spacing should not be more than, as per code, more than 3D or or 300, whichever is less. Okay. Also check minimum and maximum amount of reinforcement, which is given in page 46 IS 426 2000. The nominal cover is considered the 15 mm to 20 mm. The standard is 15 to, although the cover depend on, nominal cover depend on exposure condition, but normally we consider 20 is the standard, 15 to 20, 25 also you may consider. Effective span is also calculated using the clause number, this reference page number 34 and 35. Okay, that I shall discuss later when we will discuss the design example of 2A slab. And this thing you note, for the sake of convenience in the calculation, 1 meter width is considered. So here we complete the theory of slab. In the next lecture I shall discuss how the 2A slabs are designed. On design examples I will consider, and we design the 2A slab, and all the codal provisions we shall explain. Okay, here I end my lectures.